We start to learn the so-called diffusion frame. Basically, the idea for diffusion frame is completely different. The basic definition for diffusion frame is completely different from the premise frame. As we describe the premise frame, we say the fuel and the oxygen, okay, they are initially mixing together. Then we are talking about premixtures. Then you ignite it, then you can create a premise flame, and this flame is moving, is propagate. Okay, this is very important. Can be compared with the characteristics for the diffusion flame. Basically, the diffusion flame is defined as the fuel and the oxygen are separately supplied from the flame in different sites. Okay, the diffusion flame basically separate the flame and the fuel and the oxygen in different sites. They do not mix together. They meet only at the flame positions. You can see from these figures, this is just a simple coordinates for a given diffusion flame. You can see there is this is the chemical reaction rate, right? There is a chemical reaction rate increase to a very high value, then they drop in both sides and they represent this the location of your diffusion flame. And you can see how the chemical reaction occurs for diffusion flame depends on the supply of fuel from the left-hand side and also the supply of oxygen, or we say oxidizer, from the right-hand side. You can see from this represents the concentration variation for the fuel and this for the oxygen. You can see this away from the diffusion flame, the variation of fuel concentration and also for the oxidizer concentration almost indetectable, right? It's very small, but when they closer to the diffusion flame, you can see there is a big decrease of fuel concentration, also oxygen concentration, to represent they have a strong gradient, concentration gradient. When you look at the concentration gradient, you find out those kinds of transport mechanism is controlled by the diffusion. Okay, you can see this mass diffusion for the fuel and the oxygen that diffuse push the fuel molecules and the oxygen molecule to meet at the region of your reaction zone for the diffusion flame. When they meet together, there is the one important thing I want to mention here. Since the supply of fuel and oxygen, they should be meet together to complete burning. In this case, actually, we think about the supply of the fuel and the supply of oxygen, they just in stoichiometric ratio. Stoichiometric ratio, that means the burning of the fuel and the oxygen complete, and they do not have any fuel and oxygen left after the combustion, right? Okay, which means for diffusion flame is completely different from the premise flame. For the premise flame, depend on the initial definition for the premixtures. We may have a dim mixture, we may have a rich mixture. For dim mixture means that after the combustion, you may have some oxygen left. For the rich mixtures, that means that after the combustion, you may have some fuel left. Okay, then we can define the dim or rich conditions. But for diffusion flame, at the flame zone, at the diffusion flame burning zones, reaction zones, you will find out at this point, you do not have the fuel and oxygen left. Okay, the fuel cannot penetrate through the diffusion flame to the right-hand side. When you have a fuel left in the right-hand side, what is happen? That will show you the fuel mixed with oxygen, right? Now you will go to the so-called premise conditions. This is almost impossible, right? And a similar way, you cannot imagine the oxygen can penetrate through the diffusion flame to the left-hand side, and they will mix with the fuel. Then still will give you some wrong consideration to the premise burning, which means for diffusion flame, this diffusion flame surface just perfectly separates the fuel and the oxygen in both sides. Okay, they do not have a chance mixing together. This is the idea we are thinking about And when you have a chemical reaction occur at the diffusion flame positions, now the chemical reaction proceeds, and they will release heat to let you have a maximum flame temperature just at the diffusion flame position. Okay, there is the maximum temperature here, and those heat or those thermal energy will be diffused to both sides of a fuel and oxidizer. That means included products. Okay, this is you can see this curve represents temperature variation and also the concentration of your products. For example, carbon dioxide or water. Okay, they will go through this plot to tell you they will start to the maximum value at the diffusion flame positions. Then they will reduce in both sides. That means that they will diffuse out to the both sides of the fuel and the oxygen. People will say that actually you will find out from the plot at the diffusion flame position, there is some oxygen will penetrate through the chemical reaction to reach to a certain distance, a little bit away from the diffusion flame, right? Similar way, fuel will penetrate here. Yeah, this is true because we are dealing with a so-called finite rate of chemical reaction. Ideally, for an infinite rate of chemical reaction, you understand when the burning or your diffusion flame under infinite rate of chemical reaction, they will finish the chemical reaction in an infinite small time, right? All the fuel and the oxygen will be completely consumed without any depth, any fuel or oxygen depth. Okay, in this sense, the plot in this figure, they will just meet at a 0 point. Okay, but in reality, since they need to have a finite time to finish the chemical reaction, activation energy is a certain big value, but not an infinite large. Therefore, you need to find out here. We plot it as there is the region. Okay, this is the region to finish the chemical reactions, which means the fuel will go to reduce to a small value, and in the reaction zones, they will continue to decrease to the minimal values at the boundary of the oxygen supply. Okay, similar way, the oxygen will completely deplete at a little bit at the boundary of the fuel supply site. Okay, this kinds of extended burning, small value left in the oxidizer side or fuel side, we say this is so-called leakage. Okay, but those leakage are very, very small, and they should complete finish in a small distance away from the diffusion flame locations. Otherwise, they will cause some so-called mixing problem, right? The fuel will mix with oxygen in the right-hand side, and then this is the natural. They may have a premise flame in the right-hand side of the diffusion flame, but we did not see it. Okay, in reality, actually those kinds of leakage are very small, and they will finally be completely consumed in the oxidizer side or fuel side if we have some leakage. Okay, this is a typical structures for you to understand the combustion catalyst or diffusion flame mainly controlled by diffusion transport. Okay, you can see the mass transport depends on the concentration gradient, and the thermal transport is depend on the temperature gradient. The products still show you they can diffuse out from the flame positions to the both sides. Okay, in these structures, they give you the three important ideas. Later on, we will discuss it one by one. The first one, the flame zone still thin. Okay, the chemical reaction rate even is finite, but is still finished at a short time interval, or we say is a short distance. Okay, the flame thickness is thin. Okay, and since the flame thickness is thin, then high temperature zone is very thin. Okay, the second one, you can see those transport mechanism controlled by the diffusion process. Then you may see there is the high gradients of temperature and concentration. Actually, it is very interesting to tell you, if you look at the temperature and also the concentration profile for a given diffusion frame, you can see if you take half of the figures, the left-hand side you can see is very similar to the concentration variation and temperature profile for a premise frame, right, in the upstream side. Okay, people sometimes think about diffusion frame is just put some copy of the temperature profile and the concentration profile from upstream to the downstream through the premise frame. Therefore, people always emphasize the diffusion frame is double influenced by the diffusion transport because those diffusion transport coming from the left-hand side and then to the right-hand side. But for premise frame, actually, those kinds of diffusion transport are very important in the preheating zone. In the preheating zone, the frame, the upstream side of your premise frame, right? So that means from the figures you can imagine there is the double influence coming from the diffusion transport on diffusion frame. The third point is very important, and I want to mention there is no propagation speed. Okay, diffusion frame will sit in a certain position depends on the supply of fuel and oxygen. They can meet together and under stoichiometric proportion. Okay, this is very important. But for the stabilization of premise frame, basically is controlled by the balance between the frame speed and the flow velocity, supply velocity, right? Okay, you need to remember those kinds of definition, and you can figure out the major difference on combustion catalyst of a premise frame and a diffusion frame. Let's go back a little bit to look at a very simple diffusion frame, which is the Bunsen frame. Okay, this is a Bunsen frame I introduced very earlier in a short time, but now I can give you more descriptions about the basic diffusion frame of candle frame. Okay, look at candle. This is a very nice cartoon to show you a burning of a candle frame, right? Candle basically is a solid hydrocarbon fuel, okay, wax. And initially, when you ignite, you may have a flame burning on the top of the candle. When you have a flame, this flame is burning, then they will release heat. Those heat will transfer to the solid wax, right? When this solid wax absorb heat, they start to melt, typically on the top of your candle, okay? They melt, which means the solid wax to melt becomes a liquid wax. Okay, liquid is moving. Okay, liquid has a movement. Now, in general, for a candle, you always have a wick, right? Wick is basically the porous medium. Porous medium means that when you have a liquid wax, they will have some possibility to move. Those liquid will move around the wick and by so-called capillary actions. When they move, they will go through the wick and move to the interior in the inter region of your flame, right? Okay, here you can see there is the liquid wax, and the liquid wax will move along with the wick to the center portion of your candle flame. Usually you can see there is the pool of wax liquid, and sometimes those liquid will move flow out and to produce some kinds of teardrop. Okay. Now the next step, when you have a low side liquid go through the wick in the interior of the candle flame, you will find out they continuous because those liquids exist on the wax, right? And they continuously receive the heat from your candle flame. Now this liquid will go to the next step of gasification. They will produce the vapor of wax, okay? And the lost vapor basically is a hydrocarbon fuel. Now we try to let you have some observation. If you take a piece of the candle flame, okay, something like this, okay, you take a piece of the candle frame surface, and we assume the left-hand side is the interior region, the inner region of your frame, and the right-hand side is outer region. You can imagine in the center of your frames, of your candle frame, they will have some vapor, wax vapor, right? Because they gasify, and those molecules will move from the center to the surrounding. Okay, that means that they move to the frame positions. Here you can see the gaseous wax molecule move from the center to the frame positions. This is diffusion frame. We will describe it, give you the definition. And you also see there is some oxygen molecule moving from the outer surrounding. They meet together just at the frame positions, then start to have a chemical reactions. When they have a chemical reactions, they will release heat, okay, because temperature is high. And usually in the vicinity of frame surface, there is some unburned carbon particle, and under carbon particle under high temperature regions, they will release heat, okay, release light, okay. Heat or light represent the thermal energy output, right? Okay, at the same time, because they finish chemical reaction, carbon dioxide and the water coming out, then will diffuse from the flame zone to the outer surrounding or into your interior of the diffusion frame, candle frame. And by this kinds of mechanism, you realize we can say this is a purely for this piece of candle frame is purely is diffusion control. Then we call this so-called diffusion frame. Remember, the whole chemical reaction mechanism is like this: the gaseous wax molecule coming from the left-hand side, from the center, diffuse to the flame positions. Oxygen from the outer surrounding diffuse to the flame position. They meet, burnt, and release heat, and also those products will be diffused out from the surrounding also to the interior, the inner region of your diffusion frame. This is a basic mechanism you can figure out. For example, I need to mention here, this candle frame is basically under in a quasi environment. That means that you do not have any flow. That means that you do not have all the so-called flow convection. All mechanisms controlled by the diffusion process. Therefore, we call this as a diffusion frame. Since the diffusion frame, but you still can see the influence coming from the flow convection, right? And we say candle frame is a typical, mainly diffusion control frame because all the combustion characteristics controlled by the steep gradient of the concentration and also the temperature, okay? But you have some experience when you do the experiment, when you close all the window in your room, then the frame, the frame shape of your candle frame are quite stable and very nicely has a smooth surface. But when you open your window, or maybe you give a strong breeze, those kinds of flow, that means the flow convection coming in, when you have a strong breeze on the surface of your frame, you can see there is some wrinkle occurs on the frame surface, right? You remember, as we described for the turbulent premise frame, those eddy coming from the turbulent flow. If you have a small intensity, turbulent intensity, that means, for example, you just has a small breeze, those kinds of breeze will produce a large eddy, small fluctuation. Those eddy will give you some wrinkling on your frame's surface. Okay. Now this is the typical so-called the flickering of the diffusion frame. And later on, I will tell you this kinds of flickering motion has some influence coming from different kinds of AD occurrence. And very interesting, they can have a theoretical appearance on your frame shape. But anyway, you can look at the candle frame, you can figure out, because this is a a candle flame is purely a diffusion control flame and easily to be influenced by the flow convection. Flickering is one of the important appearance. You can figure out the influence coming from the flow convection. The second point I want to mention, usually for diffusion flame, you always can see the so-called yellow flame. Okay, why we always have a yellow flame? Yellow flame means that there is a large amount of carbon radicals accumulate inside of your diffusion flame. As you remember, the definition for diffusion flame, basically we separate the fuel inside of the flames and oxygen outside was surrounded by diffusion flame itself, right? And we analyze there is some gasification of your wax, liquid wax, to become the wax vapor. And you understand in the high temperature regions, the vapor will start to dissociate, decomposition to carbon and hydrogen. And in the inside of the diffusion flame, since you do not have oxygen, oxygen was complete broke from the outside by the diffusion flame. Okay, oxygen cannot diffuse into the interior of your diffusion flame, which means inside of the diffusion flame, you absolutely no oxygen exists. No oxygen, that means that those kinds of intermediate carbon or hydrogen cannot complete chemical reaction to become carbon dioxide or carbon monoxide or water, right? In this sense, because they are freely, because through the decompositions, then they are freely released, but they do not find the oxygen to complete reactions. Carbon has a chance to meet with carbon, and in this case, the carbon molecules they meet together, then congregate together, and they will become a large carbon particle. Carbon particle means it's a very similar to the so-called the coal, right? When you burn the coal, you will see there is a thermal. There is the surface reactions to let you see the reddish or yellow color on the surface of your coal under burning. Then, which means when you have those carbon particles exist inside of your diffusion flame, they always give you the yellow color to represent that there is a high concentration of carbon particles. Especially when you look at your diffusion flame in normal condition, this is a normal condition, which means this diffusion flame is under the influence of gravity. Look at this flame. In the flame zones, the temperature is pretty high, right? But in the surrounding temperature is low, and high temperature will give you the low density condition, and low temperature will give you the density is high. Then you will see this temperature difference will induce the density difference. Those density difference will give you the so-called the natural convection. Okay, natural convection, buoyancy effect. This buoyancy effect will push your molecules, gaseous molecule, to move upward. Okay, to move upward. And you can see here for the candle flame, you can see very clearly on the top region of your candle flame show you very bright yellow color flame, right? Since there is a high concentration of carbon particle accumulate on the top. There is the two reasons. There is a nucleation of carbon particle because they do not have oxygen inside of the diffusion flame. This is the one main factors. The other one is there is the buoyancy effect to push all the carbon particle to move to the downstream. Then the concentration will be increased by buoyancy effect. These two effects will enhance the production of carbon particles. Usually, when you see these kinds of yellow flame, we say this is so-called a sooty flame. The soot represents there is some concentration of carbon particles. Usually, when you look at detailing on the tip of your diffusion flame, sometimes the flame on the tip of the candle flame, they will release a small amount of black particle out of the tip, right? If you observe it, actually this tell you when you have a large amount of carbon particles accumulate on the tip of the candle flames, they accumulate too much, then they need to push out. When they push out, they will meet the low temperature region, then carbon return to their black color. Okay, this is the evidence for you to know those kinds of black carbon particles coming from the interior region of your candle flame. And you will see there is a very interesting experiment when you use the same candle and burn it in the outspace. Outspace, that means the microgravity or gravity is almost neglected. You will see the candle flame become like this. It's very nicely to tell you there is a diffusion flame. Okay, and the influence come in the buoyancy and accumulation of a carbon particle become separate or was suppressed, and you cannot see the yellow color. And this is a very nice typical diffusion flame without the influence of the buoyancy effect. And you can see this is a thin diffusion flame. Okay.